Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Research-University relations, and as a continuing part of our series on software engineering, and on behalf of Dan Ling, John Devon, Wolfram Schulte, I'd like to welcome Professor Barry Boehm as our guest lecturer for today. Now, it's impossible to truly do justice in recognizing Barry's accomplishments in the field of software engineering as a major contributor to our government, country, and society in this important field. While his contributions and awards are really too numerous to list. So with that, Microsoft is pleased to welcome Barry Boehm, TRW Professor of Software Engineering and the Director for the Center of Software Engineering at USC. Barry.
Thanks, John. It's a pleasure to be here, and I would like to thank you and Microsoft for your co-sponsorship of our USC Center for Software Engineering Affiliates program. That basically we have a couple of meetings every year where we get together with the affiliates and address a number of research issues that we're doing and try to get feedback from the affiliate companies, which include most of the major computing companies and some of the telecom companies and aerospace companies and the like. The one that we're doing next March 15th through 18th is on model-driven development, and so if any of you are interested in that, I'd like to welcome you to come down and participate in it. So it's also a pleasure to come and talk about the economics of software dependability to an organization that I think has really probably the biggest stake in the world in trying to achieve dependability economically. Most organizations don't have as much invested in software as you do. Most organizations basically have control over most of the parameters that determine their dependability. But what I've found is that in a lot of cases, the sources of dependability challenges that you have are all these third-party device drivers and people hanging software having different assumptions to a lot of your infrastructure software. We have a groupware tool called Easy WinWin that helps stakeholders negotiate win-win requirements. And it runs on Windows, and we go out and demo it around the world in different places. And in a lot of cases, it crashes, and people point at Windows and say, why is this crashing? But, for example, in England, they had this very high-definition display, and it was communicating with Windows by more or less saying, I am 25 different displays, and totally confusing the operating system about what was going on these 25 different displays. So again, I appreciate the kind of challenges you have here in trying to achieve dependability and trying to do it in a cost-effective way. So I better go get these things. So, yeah, what we'll talk about is, what is the business case for software dependability, and I'll give an example and see what the business case is for various kinds of test tools and things like that, and then go through a number of examples of situations where people overemphasize one aspect of dependability at the expense of others and ended up with an unsatisfactory solution. And talk a bit about, what is it that stakeholders are really depending on? Are they depending on just safety or just security or just accuracy or just response time? And these things often conflict. And so again, what we'll talk about is how do you determine how much dependability is enough if you're trying to compete with other companies on not just dependability, but time to market and cost and price and things like that. The business case basically says, if you have a finite amount of resources, and Microsoft has more resources than most companies, but they're still finite, the investments in dependability are competing for resources with investments in features and response time and adaptability and speed of development and things like that. And each thing that you invest on generates curves of, what's the present value of the flows of benefits you get from putting this much feature functionality or this much dependability in versus the cost of putting all that in. And you can discount that for present value and compute returns on investments. And again, what you find is that the values of the benefits vary by who you are and what you're responsible for. So let's take an example. Suppose you are approached by a vendor who says, we've got the world's best test data generator. We've got a track record of being able to cut people's test cases in half. What we'll do is provide you with this marvelous bargain. We'll provide it to you for 30% of your test costs. So if you're spending $1 million, we'll give this to you for $300,000. After you run all the tests for 50% of your original cost, it'll only cost you $500,000, so you're $200,000 ahead. So if a vendor came to you with this proposition, what sort of concerns would you have about it? Any thoughts? Yeah, one thing is, is this something that's been working for business and you're doing real-time control, or it's been doing things for inventory and you're doing financial or things like that? Any other? Yeah.
I effectively say we would cut my test cost in half for the same quality of test cost. It doesn't say so. But it says so, I like evidence.
Yeah. So again, what is it that's getting tested here? Is it just the nominal case, or is it covering the off-nominal cases as well, and that sort of thing? So there's nothing that's really said anything about those kind of things. Yeah.
And suppose the world should change tomorrow, and the test cases I need tomorrow are different from the ones I need yesterday. I'm going to have to go back to these guys and renegotiate. You don't really know how well this thing works incrementally. So if you change 10% or 1% of your code, you have to go back and rerun all the tests, or can it figure out which ones have been affected by the change and tell you which ones? So again, there's those kind of. Okay, well, those cover a number of things. So the one I'm going to focus on today, though, is really that the test data generators are value neutral, as are most current software engineering techniques. So they assume every defect is equally important. And most requirements tools or object-oriented methods assume that every requirement, every use case, every object, every defect, every test case is equally important. But usually what you find is that 20% of the test cases cover 80% of the business value that's at risk and that you're trying to do these tests to avoid. So here's an example from one of the testing trade journals of an organization that found that they had 15 types of customers, and for each customer type, after they did the tests, their defect, their complaint rate went from 25% down to 10%. What they had been doing was basically treating every customer as equally important and generating value at a linear pace. But what they found was that one type of customer was accounting for 50% of their billings, and that if they focused on the most business important tests first, that they could generate a lot more return on investment. So if you look at this, fundamentally, if you had bought the automated test data generator, you'd be $300,000 in the hole here. It would take you 60% of the tests to break even, and you'd end up with $200,000 ahead. If you did value-based testing using an 80-20 kind of approach, after you get to about 30% of the tests, you're $580,000 ahead in terms of net value. So again, there's a lot of benefits that can come from doing value-based testing. Another challenge, though, is that in a lot of cases there is no one-size-fits-all definition of what value is. For somebody doing customer billing, accuracy of billing and avoidance of sending the wrong bills to the wrong people and things like that are important. In other applications, safety is more important, or security, and that sort of thing. So there are a lot of different attributes of dependability that if you're starting up a new product, are important to address. Again, each one of these, like performance, tiers down to response time and resource consumption. So it's complicated from that standpoint. It also means it's more complicated because the value attributes are scenario dependent. We once worked on a project where the client said, we want 5-second response time in normal daily operation, and we want 2 seconds response time in a crisis. Well, what happens in a crisis? People generate more transactions per second. The transactions are more complex, and so things are going to get slower rather than faster, unless you do something else like minimize the non-essential messages or things like that. And the value attributes often conflict. So if you want safety and robustness and fault tolerance, what you want to do is spread data around so that if one thing crashes, you can recover it from somewhere else. If you want security, you don't want to spread data around. You're increasing your vulnerability to penetrations and things like that. And if you do a lot of fault tolerance checking and security checking, you're compromising performance. And so, again, there's a lot of trade-offs that make this a challenging problem. One of the things that we've been trying to do is to one of our agendas is really value-based software engineering. So what we're trying to do is take some of the value-neutral approaches and come up with new definitions of what does reliability mean and things like that if different people rely on different things. And so this got us involved in looking at who are the stakeholders in a typical software application. And again, some of the people are people that are supplying information into the system. So when you make a purchase with your credit card, you're supplying your credit card number. You qualify for something, you give them your social security number, and again, you're not doing anything else with the system, but something of yours is at risk. there are situations in which you're, again, not part of the customer set or the developer set, but you are flying on the plane that is being controlled or air traffic controlled by somebody else's software. So you have a stake in things. There are people that do value-added services, like financial people that collect various things and tell you which stock to buy or that sort of thing. There are people that consume information either for making decisions or playing video games or whatever it happens to be. There are people that control missions like pilots or distribution controllers or network managers or things like that. And then there are the people down here that develop and acquire and administer things. So this win-win negotiation system that we have is something that we've used on over 100 projects, and one of the nice things about it is that it electronically captures the win conditions that people put in about things like their level of service attributes or quality attributes or dependability attributes. And so we can analyze what kind of stakeholders depend on what kind of thing. So this is a little bit messy, but fundamentally what you can see is that among all of these different stakeholders that we mentioned and all these dependability attributes that we mentioned, that there is no uniform profile that says, yeah, everybody thinks privacy is important. Some people feel it's really important, some people don't care. So again, there is really no one-size-fits-all approach. Another thing that we do with this, though, is nowadays when people are negotiating levels of service and win-win agreements about how much safety do we need, how much security do we need, we provide this as sort of a starting point so that they know if you are this kind of stakeholder, you ought to be concerned about the following thing. So again, a stakeholder value definition of what dependability is sort of elaborates on the standard definition that IFIP Working Group 10.4 came up with that said dependability is something that guarantees people that if they are relying on various kind of user services that they can depend on them being there. So again, it's a vector of attribute levels and priorities that reflect what the success-critical stakeholders are depending on their utility functions, which, again, may vary across different scenarios. So if you have a crisis scenario, you're going to get a different kind of performance and importance of getting a particular response time than if you're in a daily operation. So yeah, here's another example. One of the research projects that we're part of is the NASA High Dependability Computing Program, which part of what I've been discussing is that a year into the program, people said, well, dependability is the middle name of this program, but nobody's defined what dependability is, and we try to do that. So all the stuff that I mentioned was an attempt to try to come up with better ways to define and reason about the various attributes of dependability. But one of the things that the Earth Observation Distributed Information System found was that the operators were being incentivized on minimizing downtime. The users wanted fast response to queries. If you want to know how fast the corn is going to grow in this county in Iowa, you want to know it in time to do something about it. What was happening was that the operators were optimizing availability, but they were doing it in a way that the users would get 2-week response times on a number of their queries. A lot of times that was too late to do anything about the corn or whatever else was being observed on the Earth that was important. So typically, if you get a win-lose situation, the people in a losing position tend to do something to compensate for that usually turns into a lose-lose situation. So what the users did in this case was if they thought there was something they were going to need 2 weeks from now, they would submit a whole bunch of queries about it so that if they needed that, they would be getting an answer for it, but 90% of the things they asked for weren't getting used. So the operators were finding that their workload was growing, and coping with it was not a fun thing to do. So again, what we've been trying to do is come up with value-based definitions of reliability. That it says a system provides reliability to the extent that it maximizes the probability that the system will provide stakeholder desired levels of service. So again, what we try to do in this WinWin system is ask people what is your desired level of service, but also what is your acceptable level of service. I'd like 1 second response time, but I'll settle for 4 seconds or something like that. So what this gives people is sort of a trade space in response time and security and safety and the like that they can operate within with respect to a system's operational profile. And again, one of the profiles is crisis, another one is normal day-to-day operation, and so again, you need to say, what do you want in a crisis, and if it's better than what you want in a normal day, what are you going to do with your workload to make that possible? What this implies is that the same system will have different values for reliability across different combinations of stakeholder priorities and different operational profiles. And again, the usual thing that you hear quoted is the mean time between failures of our system is 10,000 hours. Well, what does that mean? Again, it usually means that somebody has come up with some one-size-fits-all definition of failure that says it's system crashes, and if it's a crash of offline services versus online services, that's just as important. If it's something that can be instantly recovered from, that's just as important. And again, in most cases, those are not equally important. And things that don't crash, that give you the wrong answer and things like that are not counted. Again, what we're trying to do is provide counterpart definitions so that people can reason about things in a value-based way as well as just sort of a value-neutral way. So let's sort of summarize where we've gotten to from here, that there is no universal dependability metric like availability or reliability to optimize. That if you're going to achieve it in a way that your system is going to succeed, you need to identify who are the success-critical stakeholders and what are their priorities. So again, if some of them are these users that want fast response time and you neglect those, you're going to end up with a system that it generates a bunch of unnecessary workload. You need to balance satisfaction of stakeholder dependency. So again, what we find is that doing stakeholder win-win negotiation is one way of doing this. Another way is to do various kinds of trade-off analyses between reliability and cost and schedule and response time and things like that. And so one of the things that means is that you'd like to have some value of dependability models, methods, and tools. So I'll show some things that we've been doing in that area. In front of this in some way. There we go. So okay, so we've talked about the business case for software dependability. We've talked about what are stakeholders really depending on. Well, let's talk about, what does software dependability mean if you're in the marketplace competing with a bunch of people offering similar services? Is market success a monotone function of dependability, that the more dependable it is, the more money you make? Is quality really free? There's a classic book by Philip Crosby called Quality is Free that conditioned a lot of people to assume that everything they did on quality was not going to add to their bottom line. Is faster, better, cheaper really achievable? Again, we were doing this research for NASA, which believed in faster, better, cheaper, and ended up with a couple of Mars missions that crashed, and that they were doing it faster and cheaper, but not necessarily better. And again, looking at value-based versus value-neutral method. So here is an interesting curve that comes out of some work that Michael Porter, who is at the Harvard Business School and has written a couple of classic books called Competitive Advantage and Competitive Strategy and the Competitive Advantage of Nations. When I was at TRW, one of the things that they had us do is to go to Michael Porter's school and learn how to reason about things like cost and quality. And what he had was a curve that really sort of covered the middle of this, that fundamentally said that for most kind of products, you had a choice of being the cost leader and delivering acceptable quality and basically competing in the cost-constrained part of the marketplace. Or you could go for the high-quality part of the market where people were less concerned about cost but wanted the most high-quality thing. TRW at the time was over here. It was building all sorts of ultra-reliable satellites and things like that. And people were saying, well, we need to compete with the lower-cost people in our market sector. So why don't we just reduce our quality a bit and and reduce our costs a little bit? And what Michael Porter said is that there's a place in the middle here that you're not cheap enough to compete with these people, and they will wipe you out, and then you've lost your ability to compete on the high-quality sector. And so in a lot of market sectors, that shape is true. And again, if you try to make it too cheap, basically people will throw up when they see your thing and go off and buy something else. And if you're too high quality, then you get so overpriced that very few people can afford to buy what you're selling. So one of the things that we've been doing is coming up with approaches of using risk to determine how much is enough of doing testing or doing formal methods or doing requirements traceability or COTS evaluation or things like that. Basically what this involves is reasoning about risk exposure, which is basically the probability of incurring some kind of loss times the size of the loss. And again, the loss could be financial, it could be reputation, it could be future prospects and things like that. Most of these tend to be more or less independent, so these are expected values, and you can add them up into an overall risk exposure. So suppose that you're saying, we're trying to figure out how much testing is enough. When should we freeze the product and start rolling out the machinery to produce 50 million boxes or things like that? So the loss due to unacceptable dependability says that if you try to ship too soon, you're going to have a lot of defects, so your probability of loss is high, and a good many of them are going to be critical, so the size is high. If you continue to test, and again, if you do value-based testing, you can avoid getting linear gains here, but you can get 80-20 kind of gains. Eventually you get down here where there's few defects and low probability of loss, and they're minor, so there's a low size of loss, but it's taken you a long time to get there. So there's this other thing that says, yeah, what's our loss due to market share erosion? It took us a year to get here, and in that year, 3 other people introduced competitive products, and there's only 20% of the market size available to capture at this point. Then you've gone from a situation where shipping early is you've got few rivals and then they don't have very good products to a situation where you've got a lot of rivals and then they're already very strong in the marketplace. So again, these risks add together. So if you sum the risk exposures, you get this curve here that basically has a sweet spot, which is a good operating point for how much testing is enough for this particular kind of product situation. If you're building a safety critical system, typically what happens is that defects are going to cause loss of life and health and big recalls and big lawsuits and things like that. And so the size of loss due to defects goes up, and so the sum of that curve plus the market share curve moves up and to the right and says that, yeah, that how much testing is enough for this kind of company is much more important. On the other hand, if you're an internet startup, the biggest source of loss is delays in the marketplace, and again, you can afford to ship something that's less dependable early, and again, the sweet spot moves over to the left in this particular case. One of the things that internet startups sometimes forget is that they're not going to stay startups all the time, and once they have built up a customer base and things like that, people are going to be more concerned about quality and things like that, and this other curve is going to start moving up and requiring them to move to the right in terms of quality or how much testing is enough. One thing you'll notice, what are the units and dimensions on them? Yeah, well, they are typically dollars or expected dollars and months over here, but you'll notice there's no scales on these, and so later on I'll show some more quantitative things that we've done with the Kokomo model that enable you to put actual numbers in there.
If you were a monopoly, you should never ship, right?
A re-monopoly.
It's unwise to try to compete on both cost, schedule, and quality. Some exceptions, major technology or marketplace edge. So yeah, if you have a monopoly, then you can move along that dependability segment with a lot more freedom than somebody that has a lot of equal competitors that they're competing with. So in some parts of the Microsoft product line, there's a lot more freedom than others. And again, so that says there's no one-size-fits-all cost, schedule, quality strategy. So your strategy for Windows is going to be a little bit different than the strategy for your new search engine or things like that. Risk analysis is something that helps determine how much is enough of things like how much prototyping should you do, how much formal verification, how much COTS evaluation, things like that. So, and how much documentation should you do? What's the risk of doing more, and then what's the risk of doing less, and then typically you can find some sweet spot in the middle that gives you a good operating point for how much of this is enough. Another thing you can do if you're not sure about that is to buy information and say, yeah, well, if we're not sure just how this search algorithm is going to scale up, well, we spend a lot of time prototyping to verify that it's going to scale up before we commit to it. Again, it's often difficult to determine these parameter values. In some cases, a lot of companies have found that they can do quite well in just getting consensus on a scale of 1 to 10 of what's the relative risk and the relative loss, and help those and determine priorities from that. There are a number of things that the constructive cost model version 2 can help do. It's a model that is calibrated to do 161 projects that cover things that computer companies and software companies and aerospace companies have done. And each one of these projects rated itself on whether its required reliability was very low, and that the effect of a defect was a slight inconvenience, or that which basically was equivalent to a rough mean time between failure of about an hour, or something that was easy to recover from. So if it crashed once a day, that was okay. Or something that was a moderate recoverable loss, that something that crashed once a month was okay, to high financial loss and loss of human life. So again, each of these projects calibrated themselves or rated themselves on this scale, and we did a data analysis and a multiple regression analysis to see how much of the variance was accounted for by applications experience and tool support and process maturity and things like that. And for required reliability, what we found was that the slope of this curve was about 10% per increased cost per level that you were going up here. So this is the net product of two trends. That one of the trends is that the more quality that you want, the more rigorous you need to be about the requirements and the architecture and the coding and the testing and things like that, and the more thoroughly you need to invest in testing and so forth. On the other hand, there's another trend that says, the more rigorous you are about requirements and architecture, the more defects you get out early when they're cheap to fix, and so that tends to drive this cost down. But the net effect across these 161 projects was this kind of slope. And it goes, it gets a little bit more expensive per line of code going from commercial quality leader to safety critical. So again, what this says is that it provides a sort of a way of reasoning about how much it's going to cost you to. Yeah, question.
This is the cost per source instruction.
Yeah, this is
what happens if you need more source instructions to be safety critical and recover from all the baddies, and hang up your hand in disgust and break. Does the code get bigger when you want to get to the high reliability?
Yeah, one of the things that we are doing for the Federal Aviation Administration right now is building a computer security extension to Kokomo 2. And for security, some of the things that they are requiring in terms of certification go beyond what some of the safety things do. And also for all of the security functions like encryption and access control and intrusion detection and all that sort of thing, you're adding more lines of code. So the Kokomo 2 extension is addressing how much bigger is the product getting, and then per line of code, how much more expensive is it getting. Yeah, thanks for the question. Any other questions on any of this? Okay. So again, what does that say about quality is free? Here is something that says the more quality you get, the more expensive it gets. And again, this is frequently the case. That, he used to cite the Japanese automotive manufacturers as people that were proving that quality was free, but he never really said, why is it that a Lexus costs more than a Corolla or something like that? That certain kinds of quality do cost more even with Japanese manufacturers. But what you find is that investments in dependable systems cost extra. All we were calibrating to was development costs there. So what's the situation in life cycle costs? The more buggy it is, the more expensive it is to maintain. So, and what is if you include total costs of ownership in terms of the cost of doing recalls and paying off lawsuits and things like that, what happens? So it turns out that if you have high-value, long-life systems, quality does turn out to be free. But if you're just building something to keep track of your CDs or something like that, or you're building something that is supporting a single decision that you're going to make, and a month later after you've made the decision you're never going to use that software again, then maintenance costs are not worth worrying about. So yeah, here's this life cycle cost versus dependability for the relative cost to develop. If you the calibrated Kokomo model for the reliability variable for maintenance is that over here, building sloppy software means that you've got interactions of defects and a lot of things that cause the cost per instruction to go up for every instruction that you modify or add. Over here, you get the net effect of two things, that you've driven down the cost 19% from where it was here, but you've still got to run all those regression tests to make sure that it's safe to operate. So again, the net cost is higher than the nominal there. So if you have a situation, the typical thing, I don't know what it is here for Windows, but it's probably hard to tell because at any given time you're putting new features in, and so it's hard to say what's development and what's maintenance. But the typical organization spends 70% of its life cycle software costs doing maintenance. So if you go 70% of the way between here and here, you find that again, building cheap software is not a good thing to do. If you look at total cost of owning and operating the software, and including the effect on sales if the system goes down a lot, including the effect of lawsuits and that sort of thing, if you take one case in which the operational defect cost is roughly equal to the software lifecycle cost, a good example would be the Intel Pentium chip that basically cost them $500 million to develop, and it cost them $500 million to go back and recall, so in that case, this curve says that investing in a very high level of required reliability is worth it. Yeah.
I heard you said that the $500 billion Pentium take a bad account, all the negatives from Q4 and put them to blame the Pentium.
Oh, really? I see. Okay.
Classical accounting trick.
Okay. Well, that's one of the things that is difficult to do in software metrics, is to try to figure out, what were the assumptions behind all of these numbers that you get, and that's a good point. But at any rate, as your operational exposure gets bigger and bigger, the value of investments in dependability gets better and better. So let's look at a couple of other things like is faster, better, cheaper really achievable? So there's a frequent slogan in the software area that, and I guess probably in the hardware area too, that says if you want cost, schedule, and quality, pick any two. If you are building something that is supposed to fit within this volume here, you can move this triangle up or to the right or left and get two of these to fit inside the circle, but the third one is going to be hanging out. And so, does anybody see a way to get all three?
Shrink the triangle.
Shrink the triangle, right. Yeah, so basically, if this is the cost, schedule, and quality for building 100,000 lines of code, there's a triangle for building 77,000 lines of code, at least for Kokomo, that fits within the circle. And so again, one of the things that you can do is if these are your really independent variables, then you can't have feature set as an independent variable too. And so what you need to do is something that for small systems is called time boxing, and for larger systems is something that we call cost, schedule, and or quality as independent variable. And what it says is that you need to determine, just how much dependability is enough for your particular market place. And you could do this in desired delivered defect density or some value-based equivalent. What you want to make sure is to go and either work with your users, if that's the kind of thing you're doing, or your marketing people to prioritize the desired features. And again, you can use quality function deployment or integrated product teams or stakeholder win-win to do that kind of thing. And one of the things that Kokomo gives you these days is something that is a most likely cost. So what is the probability that you'll exceed the most likely cost? Well, most likely means 50%. So 50% of the time, well, I'm sorry.
In reality.
But in reality, if you generally recognize that most initial cost estimates forget about the derived requirements and forget about requirements creep and volatility and things like that. The Standish report currently says something like 72% or something like that don't come in on budget or schedule. And even then, the ones that came in within budget and schedule frequently deliver only 60% of the features that they originally tried to deliver. So 100 is probably a better estimate than 50. But at any rate, assuming that things are relatively stable, the Kokomo model gives you an optimistic and a pessimistic estimate. And the pessimistic one says you can build this many features or this many lines of code within this cost and schedule. And again, using parametric models, using expert judgment as well is a good thing to do. So one of the things you want to do then is to, once you prioritize the features, is to try to architect your system so that it's easy to add and drop borderline priority features. And again, some of the things that David Parnas has come up with on modularity and information hiding are good ways to do this. Then you can develop a core capability to this quality level. And the core capability, again, you've got a 90% chance of making it. So most of the time you will end up with cost and schedule left over, and you can add next priority features as resources permit. So this is a model that we use on pretty much all of the projects that we currently build as campus service applications at USC. Our software engineering course, as Magna and some of the people who have taken it can testify, organizes people into 5 or 6 person teams and puts them together with somebody in the medical school who is doing maternal child care or lung pathology slides or things like that, or the architecture and finance school or the business school, to build some kind of system and take it from a 2-paragraph statement of goals down to requirements, architecture, code, testing, and transition, all in 24 weeks. And if the team sign up for 48 weeks worth of work, at the end of 24 weeks, they have a partially finished product, an unhappy customer, and a low grade. So schedule is very definitely an independent variable in this case. So all of these teams have done this, and only 2 of them have failed, and a couple of them, out of those 2, one was just an irresponsible set of students who their client went out of town, and they decided it was more important to interview for jobs than to finish the project. And the other one was a COTS product that never got delivered on time. So at any rate, this is a 94% success rate, which is a lot better than the 28% success rate in the Standish group. Pardon?
Or 0%.
Or 0%, yeah. Right. That's true. Right. So it turns out that besides this required reliability cost driver, Kokomo also has a schedule compression cost driver that says the shorter you try to make the schedule, the more expensive it gets per line of code. So it provides you with a set of trade-off curves for doing this balance of cost, schedule, and quality. So suppose you have a situation in which you need something developed in 20 months to meet some kind of event, you have a budget of $5.5 million, and you want it to have a 10,000-hour mean time between failure. What you find is that if you want all 3 of, if you want 10,000 mean time between failure in 20 months, it's going to cost you $7.5 million. If you want to only pay $5.5 million, then you've got to settle for low quality of 10-hour mean time between failure. Or if you want cost and quality, you've got to allow it to take 24 months rather than 20 months. So again, trying to get all 3 is difficult if you're insisting on a 100,000-line piece of software. On the other hand, as I mentioned, if you go down to 77,000 lines of features, then you can get this point here with the right budget, the right schedule, and the right quality. So that any questions on any of those things? How much time should I?
You have until like 3 o'clock.
Okay. So yeah, I'll jump over a couple of things and then just focus on a couple others. Let's talk about some more things like basically we have a model that uses the Kokomo inputs of applications experience and architecture and tool support and things like that, and estimates the mean time between failure or delivered defect density of a system. And I'll talk about that and then show how we can use COCOMO and COQUALMO and a value estimating relationship approach to come up with return on investment for investments in dependability. So we'll skip this, which... So the constructive quality model fundamentally says what the cost model, COCOMO 2, does is ask for you to tell it how big is the software you're going to produce, what are the characteristics of the platform. Has it got all the memory and execution cycles that anybody would ever need, or is this something that is got to fit on some little tiny piece of smart dust with a limited memory and an execution cycle or something like that, or it's got to go out at space and then it's got limitations there on power. How volatile is the platform? Project things like how well supported is the system by software requirements tools, architecture tools, design tools, code tools, test tools, and that sort of thing. And product characteristics like how complex is it, how big is the database, how reusable does it have to be, and things like that. And people attributes like what is the turnover on the team, and what is the applications and platform and language and tool experience, and those sorts of things. So COCOMO 2 will take these estimates and give you software development costs and schedule for whatever you put in for the required reliability. The COQUALMO extension takes all of those and says, this gives you a way of estimating how many defects are going to be in your system. And we've calibrated this model, and if you have a pure vanilla project in terms of all these attributes, you will typically insert 10 requirements defects, 20 design defects, and 30 code defects per 1,000 lines of code. Then if you're doing this project with people that haven't done anything in this domain before, typically the number of requirements defects is going to go up considerably. The design will go up some, and the code is going to be more or less similar. It may go up a little bit. The defect introduction model adjusts these nominal rates to give you a rate at which you're introducing requirements, design, and code defects into your product. And then there's a defect removal model here that says, how much are you investing in automated tools that are model checkers or requirements traceability tools or architecture analysis tools or code standards compliance tools or deadlock and race condition detectors or things like that. And how much are you investing in people reviews of doing formal inspections or informal inspections or walkthroughs or buddy checking or things like that? And how much are you investing in execution testing? So it has some scales that I'll show. And based on how much you invest in these, it estimates how many of the defects you're going to remove. So again, automated analysis starts over here very low. Is that you're really doing nothing. You're taking what the compiler tells you is wrong with the syntax, and everything else you're going to wait until you test to get it fixed. But again, if you've got a number of things that do more powerful compiler capabilities, more compiler extensions that do semantics checking, basic things that are doing consistency checking of the requirements and design, or doing module level checks of whether the code is consistent with the requirements in the design in various ways, or you're doing formal specification, verification, temporal logic, or things like that. Again, the more you do of this, the more it's going to cost for one thing, but the more defects you're going to get out. The more peer reviews, if you don't do anything, then all of those defects that were introduced are just going to stay there. The more you go into extensive review checklists and statistical process control, the better you can do. And again, if you don't do any testing, the defects are going to stay there. But if you do a lot of testing with highly advanced tools and model-based testing and that sort of thing, then a lot of the defects will come out. And, yeah.
Is there anything that speaks to the value of the defects that you find in that particular scale, or is that just numbers?
That's a very good question, and fundamentally, after preaching to you about value-based testing, here I am showing you a tool that is being value neutral about those. And again, we are working on an extension of this model that is going to do more value-based approaches. So one of the things that we've introduced into our software engineering course this year is an experiment where last year, basically, the checklists that people used in reviews were value neutral. Every defect was equally important. And this time we've said that, yeah, we're doing high, medium, low priority and having the clients prioritize all the features and levels of service and things like that. And then each source of defects, whether it's a misspelled help message or a failure to do backup and recovery, trying to prioritize the criticality of the defects. So half the teams are using the old method, and half of them are using the new method, and we're going to see how much value added does the value-based checklists provide. And again, yeah, here we are with every defect is considered equally important. The numbers that we've calibrated the model to indicate that basically you get a factor of about 40 going from letting all the defects go through into significant investments. And again, you can get another factor of 40 or 100 in some cases in terms of defect prevention, and getting this 60 down to something like 1. So we use the COCOMO model to, the IDAVE stands for Information Dependability Attribute Value Estimator. And what it says is that you put your information processing capabilities into a model that says, yeah, how big are the features, and how complex are they, and things like that. And COCOMO gives you a cost estimate for that. With COCOMO, you put in a set of time-phased dependability investments, and it tells you how much those are going to cost, and it also tells you how many defects you're going to get out, or what's happened your mean time between failures and availability and things like that. And then you get the clients to determine, what is the effect on your business if you have 1% versus 5% downtime or things like that. And that is something. So you get the cost, you get the achievable dependability, and you get the value of dependability, and that gives you a way of saying what are the benefits and what are the costs, and getting a return on investment. So it turns out that depending, again, on what kind of stakeholder you are, there are a lot of different utility functions for various things. So if you take response time, if you're doing real-time control, getting the commands to the real-time controller before the real-time deadline means that your value is any time before there is equally good, any time after there is equally worthless. If you're doing mission planning or competitive decision making or things like that, typically there's a place where you're so far ahead of the game that it doesn't hurt to be slow. A point where you're getting into competitive situations where delaying does have a big cost, and then over here you're so far behind your competition that waiting another day isn't going to help you much or lose you much. There are some other interesting ones that say as time goes on, your data gets better. And so doing weather prediction, the closer you get to the time that you're predicting it, the better your prediction is. On the other hand, after the weather's got here, the prediction isn't worth much. Software size is the same kind of thing. You predict it a lot better when you built it, but after that, the prediction doesn't help much. There are some things like archive data in a library or a digital library or things like that the loss is not all that much. And then there are things where you have these price levels of service. So if you want a gigabit Ethernet, you pay a certain amount for that. If you want DSL, you pay a certain amount for that. If you want plain old telephone service, you pay a different amount for that, but you get slower response time. Similarly, you can do things for availability. So the normal approach to availability is one of these S-shaped curves that says that if you're really terrible on availability, then a little bit of difference isn't going to matter much. So a good example is DBase 4. Anybody know what DBase 4? Well, there was a company called Ashton Tate in Southern California, and DBase 3 was the #2 database management system in the world. And DBase 4 got shipped a year ahead of when the quality assurance people said it should have been. And it was so buggy that they were in Chapter 11 a year later. So, again, a small amount of improvements in availability wouldn't have made much difference there. It would have gone bankrupt anyway. But there is a point over here that incremental improvements in availability are going to make a big difference, and then at some point they tail off. But there was some data that Rich DeMillo gave at a couple of reliability conferences that he'd gotten from some major companies that said in terms of their order processing systems, what was it costing them per hour of downtime? So Intel said if we're down for an hour, it costs us $275,000 in profits. Amazon.com, that's at $27K, and eBay said $3K. Again, it depends on your volume, it depends on how sensitive your customers are, whether they're mass buyers or individual buyers and things like that. But at any rate, you can come up with these linear approximations that say for a lot of organizations you can come up with a cost per hour of downtime and get a reasonable value estimating relationship for availability. So fundamentally, what we've done is to take the COCOMO model's estimates of how much extra does it cost you compared to the very low to get increments in reliability, and typically the investments in peer reviews and automated tools tend to pay for themselves, and then the place that the added cost usually comes is in the added testing that you need to do. And, basically, going from nominal to high is going to add 12% to the amount of time that you're going to take testing the system. The defect removal rate that comes out of the constructive quality model basically said that you were going to decrease the defect rate by a factor of 2 for each level that you were improving things here. So fundamentally, that defect rate more or less correlates with probability of loss. So you can use that curve to approximate probability of loss. And for various companies, you can come up with a curve of what's the size of loss as a function of market share erosion. And so what we've done here is put in one for early startups, one for commercial, and one for high finance, that they're factors of 3 bigger. And what you can see is that, and again, there's a market risk curve that goes that way. It says as the risk, the size of the loss goes up here, that the sweet spot for how much testing is enough goes up. So again, you can use these kind of models to help determine how much time should you plan for testing. When you're doing the project, again, you may find that requirements creep and shifting deadlines and things like that may cause you to revise that initial estimate, but at least it can get you in the right ballpark at the beginning. Again, that was assuming that you were using value-based testing. If you do value-neutral testing, then you have a flat line there, and what happens is the sweet spot moves over and up, and so it's going to cost you about, your risk exposure is going to go up about 40% by doing value-neutral testing. Again, we've done things like this for NASA and in various applications that say how much investment in required reliability is enough for various kinds of software. So if you're planning a lunar biological laboratory, there are some things that are mission critical that if the software is wrong, it contaminates the atmosphere and the experimenters lose their health and their lives. There are a number of things that are online operational software and offline support, and putting numbers into this model indicates that going from nominal to high produces a positive return on investment for offline support and a negative one for going from high to very high. Online operational, going from high to very high is a positive return on investment, but negative for something beyond there. And mission critical means you really want to do an extra high level of dependability for that. So again, what this can help you do is to determine what number you put in for an availability requirement for different parts of your application. So it used to be NASA would sort of, what number should we put in? Should we put 4 nines or 5 nines or something like that? Then this says that it varies by what kind of software you have, and it gives you an algorithm for determining what is at least a good going in number. So again, to conclude all of this, there is no universal information system dependability metric to optimize. Depending on who your stakeholders are, what their value propositions or win conditions are, you get different answers. There's an increasing need for these kinds of things that basically software is getting more and more critical to everything that everybody builds. And so if you're building cars or radios and things like that, more and more of it is software. And determining how much dependability is enough for the entertainment part of the system and the real-time control part of the system are really important. You can use risk analysis to determine how much information system is enough, and how much testing is enough, how much documentation, how much architecture analysis, and things like that. So, quality is free in a number of cases. Generally, if you have a stable system that has a lot of value at risk if it fails, and it's going to be around for a long time, but not if you have something that is going to be obsolete next week, has less at risk, and is not going to be used very long. And again, what I'm sure you're finding here is that the kind of systems that your software is going to be supporting in the future are getting more critical, they're getting more complex, they're becoming systems of systems that the originally built stovepipes need to interoperate with each other and things like that. In your case, you don't have a lot of the problems that most people have in that they're depending on COTS products that they can't see and they can't determine the evolution of. In your case, you're building most of these, and so you still have control over those. But the technology is changing faster, the marketplace is changing faster, the consumers' interests are changing faster, and things like that. So there's a lot of need to balance discipline and agility, which is the subject of a different talk and a different book that we won't have time to get into. So any further questions? I think that was all we had. Yeah.
So for an organization like Microsoft, we've got a lot of different quality practices we can adopt. And if you look across the whole company, gosh, you got everything here. Somewhere at Microsoft, you got people doing anything. The problem that we have is we're not able to be reflective on how successful or how well we're doing because we're not gathering these metrics. And we kind of, like we look at Kokomo and we say, okay, well, these are good general guidance, but I can't really decide whether to adopt this particular Microsoft tool and invest the time or not. What are you seeing as the adoption rate and the barriers to adoption to companies spending the time to really collect like kind of Kokomo quality of time and defect data?
Here again, it varies a lot, and it varies a lot within companies. A good example is Hewlett-Packard. At one point in the late 80s, their CEO said, we're great on hardware quality and we're terrible on software quality. And they put software quality and defect rates into every division general manager's bonus criteria. And they got people like Bob Grady to do a corporate-wide metrics effort, and again, they use this FERPS approach of functionality, usability, reliability, supportability, and so forth. And so they decreased their defect rate by a factor of 10 in 5 years. Then a new CEO showed up, and it started degrading, and the stovepipes and the market pressures decreased their dependability. Again, they brought Rich DeMillo in to try to fix that, and then they acquired Compact and de-emphasized it, and so a lot of companies sort of go up and down in how they do this. But Hewlett-Packard has done a really good job. At times, IBM does a very good job of orthogonal defect classification and that kind of thing. They really do keep the metrics, and they can tell you how many of the defects logic and algorithms and interfaces and timing and things like that are likely to show up at each phase gate, and if you've got too many or too little, you ought to take another look at what's happening with your process. No.
I haven't been with Microsoft that long, but I used to be with another large company that was what I might call metrics happy. And your opening statements about how metrics can go wrong, I thought only got the tip of the iceberg. And it was sort of assuming that everyone's well-meaning and working together. But of course, that's almost never the case. The presupposition, and it's more important, in your case you're just trying to predict future defects, but a lot of these metrics are used to run operations. And now they're getting baked into outsourcing agreements. So, the outsourcing group has to keep the metrics above a certain bar, and then they can cut price as much as they can, and they get to eat the profits. So then you get into this interesting gaming of the metrics. The metrics are all supposed to appear to be meaningful, but actually not be. All right. So, for example, availability is a good one. The system's always up, except when it's reported to be down. You're not allowed to report that it's down. Okay? Right. And as long as we don't have a mechanism where there's a defect in that reporting mechanism, then we're always up.
Right.
Okay. What I think is going on here is that this gaming of the metrics now in this sort of newfangled internet adversarial arrangement is actually taking over the well-intentions of this, and I would think that if the metrics are sufficiently what we call mindless metrics, then all of this is moot.
And again, there's how much metrics is enough. So what's the risk of doing too much and too little, and what's the risk of doing the wrong ones? And Jerry Weinberg had a great story about IBM. Used to give a zero defect award for the product with the least number of defects. And one year, the winner of this only had one defect. It could not compile. So, any other questions?
Well, one of the challenges in an organization like Microsoft, where the rate of technology change in terms of internal development, technology and to some extent process change is extremely high, compounded by the fact that it's across the groups. We have enormous problems establishing any meaningful baseline and things like this, because some of the changes wind up changing some very fundamental assumptions, like this post the defects getting reported back from the field. These crashes getting reported back allow some groups to focus on, say, the defects that cause the most crashes in the field. This winds up meaning that defect density ceases to be anywhere near as accurate a predictor of most users' experience of mean time between failure. And we have a very difficult time knowing how to establish baselines there. Any thoughts or directions that we might consider looking at?
Well, here again, I think there are a number of things that, again, you need to work on. How much is enough? You would like to sort of contextualize the data and say, in what context was this data gathered? And in some cases, you can do instruction testing and branch testing and things like that, and start driving your defect rate way down. All of a sudden, if you do scenario-based testing, it goes up again because you're doing a different operational profile. It goes down, and then you do monkey testing, and it goes up, or that kind of thing. So what you would like is some way of contextualizing things. And again, people have come up with 40 context variables, and again, you've got to say how many context variables are enough. And
the problem is we wind up with more context variables than data points.
Yeah, right.
You can get everything.
I am hoping we can get together on some of this. We had one of our PhD students work at Cambridge this last summer on trying to analyze some of the code churn versus defect rate things in Windows, and we're trying to do some kind of follow-up and continue that kind of thing. We would really like to do that. Okay. Yeah.
Is this work published anywhere? Is it book or papers that has extensive?
I can give you the current draft of the report. That fundamentally it will have 10 chapters, and 8 of them are written, and we're trying to get the last ones. But yeah, I'd be happy to send you what we have.
Can you throw out any big comments about things that are really good or really bad about training a Mellon team software process, as a framework for gathering metrics and revising process?
Yeah, I would love to talk to anybody who's part of that here, because again, I think you're a good independent test of how that works. But yeah, here again, what you find is that it is something that is still being validated as far as sort of the distance from the originator effect. And, what people found with Harlan Mills's clean room approach was that if you were one person different from Harlan Mills, clean room worked really well. If you were 3 people distant from Harlan Mills, it didn't work so well. And I think there's a similar thing with Watts-Humphrey. If you are Cooper Davis and really understand it and really know how to cut corners on all of this heavyweight stuff that's in the guidelines and checklists and the roles and that sort of thing, then you can make it work quite well. On the other hand, if you pick up the book and say, ooh, then again, you're going to get into this metrics overkill and process overkill kind of thing.
That seems like the problem you have with all methodologies or metrics or whatever it may be, is that people just can't keep a balance for some reason. I don't know why, right? But they lose sight that they're here to ship a product, and the focus becomes on doing TSP or doing scenario-based or whatever it is, right? Yeah. Have you run into people that have done a good job at trying to maintain the balance in these kind of systems?
Yeah, we have a book out that is called Balancing Agility and Discipline. That, basically, about 4 years ago, we started looking into agile methods and saying, there is something here that we ought to evaluate, and our affiliates, again, felt that this was an important area that they'd like some illumination on. And fundamentally, we don't want to, our guidelines for doing these courses on campus are deliberately overkill because we want the students to learn industrial best practices, but having a 300-page set of guidelines to do a small project is too much, and so we wanted to see what could we do to what's good about these agile methods that could balance all this heavy documentation. And again, what we found was that risk is a pretty good way of determining how much process is enough. In some cases, if you're safety critical or that sort of thing, a lot of process is important. I was once on a panel that reviewed the sources of crashes in ballistic missiles, and basically the main source of change was item 4 in the Agile Manifesto that says we prefer responding to change over following a plan. So people would respond to change and say, I'm going to put this patch in there, and they would not follow the configuration management plans or quality assurance or regression test plans, and the missile would crash. So again, the risk exposure is sort of, how much is at stake if you don't follow the plan. If you're doing a monthly sprint to deliver an incremental business capability, and if it's wrong, you can fix it in the next monthly sprint, then that's not crashing a missile, and then it can be much more less focused on heavyweight processes and documents and stuff like that. Yeah.
This brings up a question I've had since about your first slide, where you show the handcrafted test versus the automatic test generation, and the automatic test generation giving value-neutral tests. But I would never use automated test generation that way, and I don't think anybody would. They would take it and use it to generate tests in the area or aiming for that test generation.
There are lots of dumb people around.
Okay.
Some people can't use those systems today, so.
So, should I be reading your next book then on balancing the two? Because I don't know anybody who would either. Well, I know people who would handcraft their tests, but I think they're a minority now. And the test generation value neutral, very few people would do. How do you guide between those choices?
Well, here again, I think you try to point out the costs and benefits of each, and again, try to avoid one-size-fits-all solutions that say I'm going to do the same thing for every piece of my software and things like that. Here again, that's sort of what we're trying to do incrementally as we revamp the process research that we're doing. So what we're doing with the reviews is saying, don't just start on page 1 and treat every sentence equally important, but for the high priority requirements first, or the high priority use cases first, and look for the high criticality defects in it first, and things like that. So. Okay, good. Thank you very much.
Okay, thank you very much.